State the relationship between ultimate BOD, BO2, COD, and theoretical oxygen demand, THOD. Explanation. Ultimate BOD, BO2, represents the total amount of oxygen consumed by microorganisms during the complete decomposition of organic matter in a wastewater sample. It is the maximum oxygen demand over an extended period, usually measured after 20 to 30 days. Chemical oxygen demand, COD, represents the total amount of oxygen required to chemically oxidize both biodegradable and non-biodegradable organic matter in a sample. COD includes substances that may not be biologically degradable, hence it is often higher than BO2. Theoretical oxygen demand, THOD. Calculated based on the stoichiometry of chemical reactions assuming complete oxidation of all organic compounds in the sample to CO2 and H2O. THOD is the theoretical maximum demand and is typically greater than COD. Relationship. The three are related as follows. BO2 less than or equal to COD less than or equal to THOD. BO2 only accounts for the biologically degradable portion of the sample. COD includes both biodegradable and non-biodegradable components. THOD represents the maximum oxygen demand, assuming complete oxidation. Diagram representation. I will generate a graph to illustrate the relationship between BO2, COD, and THOD over time.
The graph illustrates the relationship between BO2, COD, and TOD. BO2, blue curve, shows the progressive increase in biological oxygen demand over time, leveling off as biodegradable matter is consumed. COD, green dashed line, represents a constant level as it includes both biodegradable and non-biodegradable organic matter. TOD, red dotted line, indicates the theoretical maximum oxygen demand, always the highest value. Let me know if you need additional clarification or further questions.
Further questions.
Q2. What is the typical range of CO-BOD ratios for biological treatment? Explanation. The CO-BOD ratio is an important parameter in wastewater treatment to evaluate the biodegradability of wastewater. It provides insights into the fraction of organic matter that is biodegradable versus non-biodegradable. One typical range for biological treatment. For wastewater suitable for biological treatment, the CO-BOD ratio typically ranges from parser 1.5 to 3 FRUS. A ratio close to 2 indicates a good balance of biodegradable organic matter. 2. Interpretation. COD-BOD 2 suggests the wastewater is mostly biodegradable, making it ideal for biological treatment. CO3 indicates a higher fraction of non-biodegradable matter, which may require advanced or chemical treatment methods. CO-BOD 1.5, rare but might suggest incomplete measurement or atypical wastewater characteristics. Diagram or graph. Would you like me to plot a diagram showing COD-BOD ratio variations and their suitability for treatment? Let me know. Q3. Compare coagulation and flocculation in terms of process and purpose. Comparison. Comparison table. Coagulation, destabilize particles into larger clusters. Definition. The process of destabilizing suspended particles by neutralizing their surface charges. The aggregation of destabilized particles into larger clusters, flocks. To break down the repulsive forces between particles, enabling their agglomeration, to form settlable or filterable flocks for removal. Process. Involves the addition of coagulants, e.g. alum, ferric salts, to neutralize charges. Gentle mixing is applied to encourage particle aggregation into flocks. Mechanism. Electrostatic charge neutralization, bridging and bonding of destabilized particles. Mixing. Rapid mixing to distribute the coagulant evenly. Slow mixing, low shear to form stable flocks. End products, destabilized small particles. Large, visible flocks that can settle or be filtered. Chemical agents, alum ferric chloride or synthetic polymers. Polymers may be used to aid in flock formation. Key points. 1. Coagulation prepares the particles for flocculation by neutralizing their repulsive charges. 2. Flocculation ensures these particles combine into flocks that can be efficiently removed through sedimentation or filtration. Would you like a diagram of the coagulation-flocculation process to better visualize it? Let me know. Here is the schematic diagram illustrating the coagulation and flocculation processes. Let me know if you need further modifications or explanations for any specific part of the diagram. Q4. Differentiate between nitrogenous BOD, N-BOT, and carbonaceous BOD, C-BOD. Definition. Carbonaceous BOD, C-BOD, represents the amount of oxygen consumed by microorganisms while decomposing organic carbon-based compounds in wastewater. Nitrogenous BOD, N-BOT, refers to the oxygen consumed during the oxidation of nitrogenous compounds, e.g. ammonia, into nitrates by nitrifying bacteria. Comparison table. Aspect, carbonaceous BOD, C-but nitrogenous BOD, N-Biogl process. Per source of oxygen demand, source of oxygen demand. Organic carbon compounds, e.g. sugars, fats, proteins. Nitrogenous compounds, e.g. ammonia, organic nitrogen. Biological process, performed by heterotrophic bacteria, performed by autotrophic nitrifying bacteria, Nitrosomonas and Nitrobacter. Time of occurrence, occurs earlier, initial phase of the BOD test. Occurs later, after for 5 days in the BOD test. Impact on results. Measured during the first phase of the BOD test, BOD5, becomes significant after the first 5 days. Application. Represents the main oxygen demand in most wastewaters. Important for wastewater with high nitrogen content, e.g. industrial waste. Phases on the graph. The C-BOD phase dominates during the first few days, while the N-BOT phase starts to contribute later. Would you like me to create a graph illustrating these phases? Let me know. The graph illustrates the phases of carbonaceous body, CB-bod, and nitrogenous bod, N-body, over time. C-body, blue curve, represents oxygen demand from carbon-based organic compounds, dominant in the early phase. N-bod, green curve, shows oxygen demand from nitrogenous compounds, starting later, around day 5. Total BOD, red dashed line, summation of C-bod and N-body, representing the overall oxygen demand. Let me know if you need further clarification or additional modifications. Q5. Explain why chemicals in higher valency states are preferred for the coagulation process. Reasons for preference. 1. Charge neutralization efficiency. Chemicals with higher valency states, e.g. aluminum in Al or iron in Fe, carry more positive charges per molecule. These higher charges are more effective at neutralizing the negative surface charges of colloidal particles in wastewater, leading to better destabilization and aggregation. 2. Formation of denser flocks. Higher valency coagulants promote the formation of denser, stronger flocks. These flocks settle faster, improving sedimentation efficiency in the treatment process. 3. Lower dosage requirement. Coagulants with higher valency states are more effective per unit weight, meaning lower quantities are needed compared to lower valency coagulants. 4. Improved performance across pH ranges. Higher valency chemicals like aluminum sulfate, alum, or ferric chloride are effective across a broader pH range, making them versatile for different water qualities. Examples of coagulants. Higher valency. Aluminum sulfate, Al2SO3, ferric chloride, FeCl3. Lower valency. Ferrous sulfate, ESO. Would you like additional visuals or diagrams to explain this concept further? Here is the schematic diagram showing the difference in coagulation efficiency between low and high valency coagulants. On the left, low valency coagulants result in weaker charge neutralization and smaller flocks, while on the right, high valency coagulants create larger, denser flocks that settle faster. Let me know if you need further clarification or additional visualizations.
Additional visualizations.
The graph illustrates the difference in settling velocity between flocks formed by low and high valency coagulants. Low valency coagulant, blue curve, flocks settle more slowly as the interaction between particles is weaker and flocks are smaller. High valency coagulant, red curve, flocks settle more quickly due to stronger charge neutralization and the formation of larger, denser flocks. This comparison visually emphasizes the faster settling achieved with high valency coagulants. Let me know if you'd like more insights or adjustments. NARC Q6. What are the important factors considered in the BOD test? The biochemical oxygen demand BOD test is essential for assessing the organic matter content in wastewater and its potential impact on aquatic ecosystems. The key factors considered in the BOD test are 1. Sample selection. The sample must be representative of the water or wastewater being tested. Temperature and time of collection are crucial as they can influence the results. 2. Incubation period. The standard BOD test typically incubates the sample for 5 days. BOD 5 at a constant temperature of 20 degrees Celsius, 68 degrees Fahrenheit, to simulate typical environmental conditions. In some cases, longer periods, e.g., 30 days, are used to measure ultimate BOD, BODU. 3. Temperature. The test is generally conducted at 20 degrees Celsius. A deviation in temperature can significantly affect microbial activity, which in turn influences oxygen consumption. 4. Dissolved oxygen, DO. The initial DO concentration before incubation and the final DO concentration after the incubation period are measured. The difference between these values indicates the oxygen demand exerted by microorganisms. The test is typically done in a sealed, airtight container to prevent oxygen exchange from the atmosphere. 5. Microbial population. Tired? The microorganisms present in the sample are responsible for decomposing the organic matter. Their activity depends on the nature of the organic material and the test conditions. The presence of sufficient nutrients, like nitrogen and phosphorus, and adequate temperature supports microbial growth. 6. Nutrient availability. Wastewater with low concentrations of nutrients, nitrogen, phosphorus, may need to have these added to prevent growth limitations during the test. Number 7. pH level. The pH of the sample can affect microbial activity. A pH range between 6 and 8 is ideal for most microorganisms. Extreme pH levels can inhibit microbial action and lead to inaccurate results. 8. Chemical interference. Certain chemicals, such as chlorine, may inhibit microbial activity, leading to underestimation of BOD. Samples must be free of chemicals that could interfere with microbial metabolism during the test. Summary. The BOD test is highly sensitive to factors like temperature, microbial activity, pH, nutrient availability, and the nature of the sample. Accurate results depend on careful control of these factors. Would you like me to create a diagram explaining the setup of the BOD test, or further details on any of the factors? Here is the schematic diagram illustrating the setup of a standard BOD test. It shows the process, including the initial and final dissolved oxygen DO measurements, incubation at 20 degrees Celsius for 5 days, and the oxygen consumption by microorganisms. Let me know if you'd like any further adjustments or explanations. It seems like I can't generate any more images right now. Please try again later. Let me know if you would like to proceed with something else, or if you'd like to revisit this question at a later time.
Draw a schematic diagram of carbonaceous BOD, CBOD, and nitrogenous BOD, NBOD, and explain the phases on the graph itself. Explanation of phases. Carbonaceous BOD, CBOD, phase. In the CBOD phase, microorganisms initially consume oxygen to decompose carbon-based organic matter, example sugars, fats, proteins. This phase occurs early in the test, typically within the first 4 to 5 days. As the organic carbon is consumed, the oxygen demand decreases over time. Nitrogenous BOD, NBOD, phase. The NBOD phase starts after the carbonaceous material is mostly consumed, usually around day 5. Microorganisms begin to oxidize nitrogenous compounds, especially ammonia, through nitrification. This phase continues as oxygen is consumed to convert ammonia into nitrates, contributing to the total BOD over a longer period. Diagram. I'll now generate a schematic diagram showing the CBOD and NBOD phases over time, with explanations on the graph itself. It seems like I can't generate any more images right now. Please try again later. Let me know if you would like to proceed with something else, or if you'd like to revisit this question at a later time.
Sure. Q8. Which types or nature of bacteria are involved in the biological treatment of BOD? In biological treatment processes for wastewater, bacteria play a crucial role in breaking down organic matter and reducing the biochemical oxygen demand, BOD. The main types of bacteria involved include 1. Heterotrophic bacteria. Role. These bacteria break down organic carbon-based compounds like carbohydrates, proteins, fats into simpler substances such as CO2 and H2O, consuming oxygen in the process. Nature. They are typically the dominant type of bacteria in the initial stages of BOD removal. Examples: Pseudomonas species, Bacillus species, Escherichia coli, in some cases depending on the type of organic matter. 2. Autotrophic bacteria. Role. These bacteria oxidize inorganic substances, such as ammonia, into less harmful compounds, such as nitrate, in the later stages of treatment. Nature. They are involved in the nitrogen cycle, particularly in nitrification. Examples: Nitrosomonas, convert ammonia to nitrite. Nitrobacter, convert nitrite to nitrate. 3. Facultative anaerobic bacteria. Role. These bacteria can switch between aerobic and anaerobic metabolism depending on oxygen availability. In anaerobic conditions, they help degrade organic matter without oxygen. Nature. Found in both aerobic and anaerobic environments within treatment processes. Examples: Enterobacter species, Clostridium species. 4. Aerobic bacteria. Role. These bacteria require oxygen to break down organic matter. They are the primary agents responsible for BOD reduction in aerobic treatment processes. Nature. They thrive in oxygen-rich environments such as activated sludge systems. Examples: Aeromonas species, Flavobacterium species. 5. Anaerobic bacteria. Role. These bacteria function in the absence of oxygen, playing a key role in the anaerobic digestion of organic matter. Nature. Anaerobic bacteria are involved in the breakdown of organic compounds in environments such as septic tanks or sludge digesters. Examples: Methanogens, produce methane as a byproduct. Desulfovibrio, reduce sulfate to hydrogen sulfide. Summary: heterotrophic bacteria dominate in the early stages of BOD removal, breaking down carbon-based compounds. Autotrophic bacteria take over later, dealing with nitrogenous compounds through nitrification. Facultative anaerobes and anaerobic bacteria assist in conditions where oxygen levels fluctuate or are absent, such as in deep sludge layers. Let me know if you would like a diagram or further elaboration on any of these bacteria types. Q9. Compare ultimate BOD, BODU, COD, and 5-day BOD, BOD5. 1. Ultimate BOD-DDU. Definition. BODU refers to the maximum amount of oxygen that will be consumed by microorganisms in the process of decomposing the total organic matter in a sample over a prolonged period, usually 20 to 30 days. Significance. It represents the total oxygen demand over time, including the degradation of both biodegradable and slowly biodegradable material. Measurement. Measured in lab conditions, typically after an extended period of incubation. Use. Used to estimate the total oxygen demand for wastewater over a longer time, especially for wastewater that undergoes slow degradation. 2. Chemical oxygen demand, COD. Definition. COD represents the total amount of oxygen required to chemically oxidize both biodegradable and non-biodegradable organic compounds present in a sample. Significance. COD includes all types of organic matter, regardless of whether it is biodegradable. Measurement. Measured by a chemical reaction, usually using a strong oxidizing agent like potassium dichromate. Use. Indicates the overall pollution level in water and is useful when assessing the need for chemical treatments. 3. 5-day BA, BO2-5. Definition. BOD5 is the oxygen demand exerted by microorganisms to decompose organic matter in a sample over 5 days at 20 degrees Celsius. Significance. It is a practical measure of the organic pollution in water and the effectiveness of treatment processes in the short term. Measurement. BOD is measured after 5 days of incubation, typically under controlled conditions, 20 degrees Celsius. Use, commonly used to estimate the biological oxygen demand in wastewater treatment systems and aquatic environments. Comparison table. Parameter ultimate BODU, chemical oxygen demand, COD. 5-day BOD, BOD5, and DMR. Comparison table. Chemical oxygen demand, BOD5 thirst. Definition. Maximum oxygen demand over extended time. Total oxygen demand required to chemically oxidize all organic matter. Oxygen demand over 5 days to decompose organic material. Time frame, 20 to 30 days. Instantaneous chemical reaction, 5 days. Measurement. Extended incubation, typically 20 to 30 days. Chemical oxidation test, standard 5-day incubation at 20 degrees Celsius. Scope includes all biodegradable and slowly biodegradable matter. Includes both biodegradable and non-biodegradable organic material. Represents biodegradable organic matter, mostly carbon. Usage, to estimate total pollution and degradation over time. To assess total organic matter, biodegradable and non-biodegradable. To assess the short-term impact of organic matter on oxygen demand. Summary. BODU measures the total long-term oxygen demand for the entire degradation process. COD measures the total oxygen demand including non-biodegradable compounds. BOD5 provides a short-term measure of the oxygen demand from biodegradable organic matter. Let me know if you need further clarifications or a visual representation. Q10. Enlist the types of solids present in water bodies. Water bodies, especially in wastewater treatment, contain different types of solids that can affect water quality. The main types of solids present are 1. Suspended solids, SS. Definition. These are solid particles that are suspended in the water but not dissolved. They can be either organic or inorganic. Types. Total suspended solids, TSS. All particles in the water, including those that settle over time. Settlable solids. Particles that are heavy enough to settle out of the water under the influence of gravity. Importance. High levels of suspended solids can cloud water and may require treatment to remove them, e.g., filtration or sedimentation. HAP2. Dissolved solids. Definition. These are solids that have dissolved into the water and cannot be separated by filtration. They usually consist of salts, minerals, and other dissolved organic or inorganic compounds. Types. Total dissolved solids, TDS. All dissolved substances including salts, minerals, and organic materials. Conductivity. The ability of water to conduct electricity, often correlated with the concentration of dissolved salts. Importance. High levels of dissolved solids can affect water taste, hardness, and may require processes like reverse osmosis for removal. 3. Colloidal solids. Definition. These are very fine solid particles that are suspended in water and cannot easily be removed by settling or filtration due to their small size. Characteristics. They typically require coagulation and flocculation to remove. Examples: clay, silt, bacteria, and other microorganisms. Importance. Colloidal particles can cause turbidity in water and may be challenging to treat. Hamburger 4. Biodegradable solids. Definition. These are organic solids that can be broken down by microorganisms. Examples: food waste, plant material, and sewage. Importance. Biodegradable solids contribute to the BOD in wastewater, affecting oxygen levels in the receiving water body. 5. Inert solids. Definition. These are solids that do not degrade or react chemically with other substances in the water. Examples: sand, gravel, and other non-reactive minerals. Importance. While inert solids may not directly affect water quality, they can influence sedimentation processes. 6. Organic solids. Definition. These are solids that originate from living organisms or their byproducts. Examples: plant and animal debris, sewage, and industrial waste. Importance. Organic solids contribute to the BOD in water bodies and may affect the oxygen demand. Non-organic solids. Definition. These solids do not originate from living organisms and are usually mineral-based. Examples: silt, sand, and heavy metals. Importance. Non-organic solids can contribute to water turbidity and affect physical and chemical properties of water. 8. Settlable solids. Definition. Solids that are heavy enough to settle to the bottom of a container or water body over time. Importance. They contribute to sludge in wastewater treatment plants and can be removed by sedimentation. Summary. Suspended solids include particles that are temporarily in suspension in the water. Dissolved solids consist of substances that are fully dissolved in water. Colloidal solids are fine particles that require special treatment. Biodegradable solids can be broken down by bacteria and contribute to BOD. Inert solids do not interact with water chemically. Organic and non-organic solids differ in their origin, living versus non-living. Let me know if you need further clarification or a diagram illustrating these types of solids. Q11. Mention the indicators used to assess water treatment effectiveness in water bodies. Several indicators are used to assess the effectiveness of water treatment in water bodies. These indicators help determine the quality of water and whether it meets regulatory standards for various uses, e.g., drinking, recreation, industrial use. Common indicators include: HAG1, biochemical oxygen demand, BOD. Purpose: measures the amount of dissolved oxygen needed by microorganisms to break down organic matter in water. Significance: high BOD levels indicate significant organic pollution, while lower BOD levels suggest effective treatment. It helps assess the efficiency of biological treatment processes. 2. Chemical oxygen demand, COD. Purpose: represents the total amount of oxygen required to chemically oxidize all organic compounds, both biodegradable and non-biodegradable, in water. Significance: COD provides a measure of the overall water pollution, and a lower COD after treatment indicates effective removal of organic pollutants. 3. Total suspended solids, TSS. Purpose: measures the concentration of solid particles that are suspended in water and can be removed through sedimentation or filtration. Significance: a reduction in TSS after treatment indicates effective solid removal and can be correlated with the removal of pathogens and other pollutants. Total dissolved solids, TDS. Purpose: measures the total concentration of dissolved substances, such as salts, minerals, and metals, in water. Significance: High TDS levels can indicate water salinity, hardness, and contamination from industrial or agricultural sources. Treatment effectiveness is assessed by the reduction in TDS levels. 5. pH level. Purpose: measures the acidity or alkalinity of water. Significance: the pH level of treated water should fall within a safe range, typically 6.5 to 8.5 for human consumption, aquatic life, and other uses. The pH can affect the solubility of metals and other chemicals in water. Matter 6. Turbidity. Purpose: measures the cloudiness or haziness of water caused by suspended particles. Significance: high turbidity indicates the presence of suspended solids and microorganisms, which can be removed by coagulation, flocculation, and filtration. Effective treatment reduces turbidity levels. 7. Fecal coliform or E. coli. Purpose: measures the presence of fecal contamination in water, typically indicated by the presence of coliform bacteria. Significance: the presence of coliforms indicates contamination from human or animal waste, and high levels can indicate the need for further disinfection processes. 8. Ammonia and nitrates, nitrogen compounds. Purpose: measures the concentration of ammonia and nitrate compounds in the water, which come from organic waste and fertilizers. Significance: high ammonia levels are toxic to aquatic life and must be removed through nitrification. Effective treatment will reduce ammonia and nitrate concentrations. 9. Chlorine residual. Purpose: measures the remaining chlorine concentration in water after disinfection. Significance: chlorine residual indicates the effectiveness of disinfection and the residual protection against pathogens. It must be within safe limits, typically below 4 milligrams per liter for drinking water. 10. Heavy metals, e.g. lead, mercury, arsenic. Purpose: measures the concentration of toxic heavy metals in water. Significance: high levels of heavy metals are toxic and carcinogenic, making their removal critical for water treatment. The reduction of heavy metals is a key indicator of treatment efficiency. 11. Total organic carbon. Purpose: measures the total amount of carbon in organic compounds present in water. Significance: TOC levels reflect the presence of organic pollutants. Effective water treatment should reduce TOC concentrations by breaking down or removing organic matter. 12. Dissolved oxygen. Purpose: measures the amount of oxygen dissolved in water, which is essential for the survival of aquatic organisms. Significance: STOW low DO levels indicate poor water quality or the presence of excessive organic matter. Effective treatment processes, especially aeration, help maintain adequate DO levels. Summary: the effectiveness of water treatment is typically assessed using a combination of physical, chemical, and microbiological indicators: lower BOD, COD, TSS, and turbidity, along with improved pH levels, decreased pathogen count, and reduced nutrient levels, ammonia, nitrates, all signal effective water treatment. Let me know if you'd like more details or visual aids on these indicators. Q12. Why is alkalinity measured? At what pH levels are carbonate, bicarbonate, and hydroxides significantly present? Q12. Why is alkalinity measured? At what pH levels are carbonate, bicarbonate, and hydroxides significantly present? 1. Why is alkalinity measured? Alkalinity is a measure of the ability of water to neutralize acids, primarily due to the presence of basic ions like carbonates, HCO-, carbonates, CO3 werleninons, and hydroxides, OH-mannans. It indicates the buffering capacity of water, which helps resist drastic changes in pH when acids are added. Purpose of measuring alkalinity: buffering capacity. Alkalinity water, ensuring that the water remains within a range suitable for aquatic life and industrial processes. Water treatment. In water treatment, alkalinity is important for coagulation, flocculation, and softening processes. It can affect the dosage of coagulants used. Aquatic ecosystem health. In natural water bodies, Adequate alkalinity helps prevent large pH fluctuations, which could be harmful to aquatic organisms. Char 2. pH levels and the presence of carbonate, bicarbonate, and hydroxides. The distribution of carbonate, bicarbonate, and hydroxide ions in water is highly dependent on the pH of the water. Here's how they behave at different pH levels. pH range, dominant species, chemical form. pH for us, hydroxide, OH tenor, dominant form of OH mints, Cheson pH 4-8, bicarbonate HCO3 minor. Bicarbonate dominates in this range. Carbonate, thiosinate CO3 carbonate predominates above pH 8. pH 10, carbonate and hydroxide, OH, both carbonate and hydroxide are present. Explanation. At pH splenge 4, water tends to have high levels of hydroxide ions, OH stents, making it highly alkaline. At pH 4 to 8, the dominant form is bicarbonate HCO3 monon, which is the main buffering agent in natural waters and helps resist pH changes. At pH 8 to 10, carbonate ions, CO3 become the dominant species. This is the typical range for many natural waters, where the carbonate-bicarbonate buffer system operates effectively. At pH 10, carbonate CO3 and hydroxide OH start ions are present, especially in higher alkalinity waters, where pH is basic. Summary. Alkalinity is important because it determines the water's capacity to neutralize acids, preventing large pH swings that could harm ecosystems or interfere with industrial processes. Carbonate, bicarbonate, and hydroxide ions are present at different pH levels, with bicarbonate being the dominant species in the typical pH range of natural waters, 6.5 to 8.5. Would you like a diagram or graph to illustrate the changes in these ions with pH? Q13. Classify pollutants based on their solid content. Pollutants in water can be classified based on their solid content into three main categories: dissolved pollutants, suspended pollutants, and settlable pollutants. Each type of pollutant has different characteristics and implications for water treatment. Dissolved pollutants. Definition: pollutants that are completely dissolved in water and cannot be separated through simple filtration or settling. Characteristics: exist in molecular form or as ions in the water. These pollutants are typically stable and diffuse evenly throughout the water. Examples: heavy metals, e.g. lead, mercury, cadmium; nutrients, e.g. nitrates, phosphates; dissolved organic matter, e.g. dissolved proteins, sugars; salts, e.g. sodium chloride. Treatment: requires chemical treatments, reverse osmosis, or biological processes for removal. 2. Suspended pollutants. Definition: particles that are not dissolved in water, but are instead suspended and can be filtered or settled with time. Characteristics: these particles are usually large and can be removed by physical processes like filtration, sedimentation, or coagulation. Suspended solids are responsible for turbidity in water, making it cloudy. Examples: silt, clay, and organic matter, e.g. plant debris, animal waste. Colloidal particles, small particles that remain suspended due to their small size. Microorganisms, e.g. bacteria, algae. Treatment: physical removal methods like filtration, sedimentation, and flocculation. 3. Settlable pollutants. Definition: pollutants that are heavy enough to settle at the bottom of a container or water body under the influence of gravity. Characteristics: these solids settle over time and are removed through sedimentation. They usually require less energy or complex treatment processes to remove compared to suspended solids. Examples: inorganic materials like sand, grit, and gravel. Organic solids such as algae, plankton, or biomass. Treatment: simple sedimentation or mechanical processes like gravity-based settling tanks in wastewater treatment. Summary of classifications. Type of pollutant. Treatment method: reverse osmosis, like gravity-based settling tanks. Pollutants that are completely dissolved and spread uniformly. Chemical treatment, reverse osmosis, biological methods. Suspended pollutants, solid particles suspended in water. Filtration, sedimentation, coagulation. Settlable pollutants. Pollutants that are heavy enough to settle. Sedimentation, gravity-based treatment. These classifications help in selecting appropriate water treatment techniques. Dissolved pollutants typically require more complex methods, e.g., chemical treatment, while suspended and settlable pollutants are often removed through simpler physical processes. Let me know if you need any further details or a diagram. Dec Q14. Define the food to microorganism FFM ratio and mention its significance. 1. Definition of the food to microorganism FM ratio. The FM ratio is the ratio of the amount of organic matter, food available for microbial consumption, to the amount of microorganisms present in the system. This ratio is used to evaluate the performance of biological treatment systems, especially in activated sludge processes. Mathematically, it is expressed as F ratio equals fraxed food organic matter input, microorganism mass. Food typically refers to the organic matter, e.g. carbon compounds, available for microorganisms to consume. Microorganisms are typically bacteria involved in the degradation process, such as those in the activated sludge. 2. Significance of the FM ratio, control of microbial growth. Dust. The FM ratio is used to control the microbial growth and ensure the proper balance between food supply and microbial population in biological treatment systems. A proper balance ensures efficient degradation of organic matter without overwhelming the system with excessive microbial growth or insufficient microbial activity. Indication of treatment efficiency. Diatat high FM ratio indicates that the system is receiving more organic material than the microorganisms can degrade, potentially leading to incomplete treatment or excess sludge production. A low FM ratio suggests that the microbial population is not being adequately fed, which can result in underperforming treatment or excessive microorganism die-off. Ideally, the FM ratio should be balanced to maintain effective microbial activity for optimal BOD removal without causing overgrowth or underutilization. Guiding design and operation. The FM ratio helps in the design and operation of treatment plants by determining the appropriate size of microbial populations needed for efficient treatment. It assists in setting aeration rates, anaerobic systems, adjusting sludge age, and optimizing organic load to improve treatment performance. 3. Interpretation of FM ratios. High FM ratio suggests that the system is overloaded with food, organic material, leads to rapid microbial growth, which can result in more sludge and less efficient treatment if the system is not designed to handle the excess. Low FM ratio indicates the system has fewer microorganisms relative to the available food. This can lead to poor treatment performance because the microorganisms may not have enough food to maintain optimal activity. Ideal FM ratio. The ideal range is usually between 0.1 to 0.5 for most activated sludge systems, which balances microbial growth and organic matter degradation efficiently. Summary. The FM ratio is crucial for maintaining the balance between food supply, organic material, and the microbial population in biological treatment systems. It helps in managing sludge production, optimizing treatment efficiency, and guiding operational adjustments to maintain a healthy microbial environment for wastewater treatment. Would you like a diagram or further explanation of how the FM ratio impacts the treatment process? Q15. What is the activated sludge process? Explain its working. 1. Definition of the activated sludge process. The activated sludge process is a biological wastewater treatment method that uses a mixture of microorganisms, mostly bacteria, to degrade organic pollutants in wastewater. The microorganisms are kept in suspension in the wastewater through aeration, and they feed on organic matter, breaking it down into simpler substances like carbon dioxide and water. 2. Working of the activated sludge process. The process involves two main stages, aeration and sedimentation. Here's a detailed explanation of each step. A. Aeration. Purpose. Aeration provides oxygen to the microorganisms, enabling them to metabolize the organic matter, food, in the wastewater. This is typically done in an aeration tank or basin where air or pure oxygen is supplied to promote the growth of bacteria and other microorganisms. Process. Wastewater is pumped into the aeration tank, where it is mixed with the activated sludge, a mixture of microorganisms that have been cultured and are actively breaking down organic matter. The air supply ensures that the microorganisms have enough oxygen to continue their metabolic activity. During this stage, microorganisms consume the organic pollutants, BOD, and convert them into biomass, new cells, and metabolic byproducts, mainly CO2 and H2O. B. Sedimentation. Purpose. After the aeration stage, the mixture of treated water and microorganisms sludge is allowed to settle in a sedimentation tank, or secondary clarifier. Here, the microorganisms sludge settle at the bottom due to their weight, and the treated water, supernatant, is removed from the top. Process. The clarified effluent, treated water, is removed, while the settled sludge is either recirculated back into the aeration tank to maintain microbial populations or removed from the system for further treatment, e.g. sludge digestion or disposal. 3. Key components of the activated sludge system, aeration tank, where the wastewater is mixed with microorganisms and oxygen is supplied for biological treatment. Secondary clarifier, sedimentation tank, where the treated water is separated from the microorganisms, sludge that settle out. Sludge recycling. A portion of the settled sludge is returned to the aeration tank to maintain a high concentration of microorganisms. Types of activated sludge systems. Conventional activated sludge, CHAS. The standard form of the process where aeration and sedimentation are used to treat wastewater. Extended aeration, EA, a variation of the activated sludge process where aeration is prolonged to achieve more complete treatment, often with a higher retention time of the microorganisms. Oxidation ditches, a type of activated sludge system that uses a continuous flow of wastewater in a circular channel for aeration and biological treatment. Advantages of the activated sludge process. High efficiency. It is effective in reducing BOD, COD, and suspended solids in wastewater. Flexibility. Can be adapted to treat varying amounts of wastewater and pollutants. Relatively low space requirement. Compared to other biological treatment methods like lagoons, activated sludge systems require less space. Scalable. Can be scaled up for large municipal treatment plants or down for smaller decentralized systems. 6 challenges. Sludge management. The production of excess sludge that requires further treatment, e.g., digestion or disposal. Energy consumption. Aeration requires significant energy, particularly in large treatment systems. Operational complexity. Requires careful monitoring and control of aeration, microbial activity, and sludge production. Summary. The activated sludge process uses microorganisms in an oxygen-rich environment to treat wastewater by breaking down organic pollutants. It consists of an aeration phase, where microorganisms consume pollutants, and a sedimentation phase, where treated water is separated from excess sludge. The process is efficient, but managing sludge and energy consumption are important considerations for effective operation. Let me know if you'd like a diagram or further clarification. HAR Q16. What are the main parameters influencing the sludge volume index, SVI, in wastewater treatment plants? The sludge volume index, SVI, is an important parameter used to assess the settleability of activated sludge in wastewater treatment systems. It is a measure of the volume of settled sludge in milliliters per unit mass of suspended solids in grams in a mixed liquor sample after 30 minutes of sedimentation. The SVI is an indicator of how well the sludge will settle in the secondary clarifier. 1. Key parameters influencing SVI. A. Microbial composition of the sludge. The type and activity of microorganisms in the sludge play a significant role in determining the settleability. Filamentous bacteria, for example, can cause poor settling because they form long, stringy filaments that reduce the density of the sludge, leading to an increased SVI. Flock-forming bacteria produce more compact and dense flocks, which settle better and result in a lower SVI. B. Sludge age, mean cell residence time, the sludge age, or MCRT, is the average time the microorganisms spend in the system before being removed. A longer sludge age typically means that the microorganisms have had more time to break down organic material, leading to better flock formation and improved settleability. Longer sludge age usually results in more compact, well-formed flocks, decreasing the SVI. Shorter sludge age can lead to underdeveloped flocks that are more likely to remain dispersed, resulting in a higher SVI. C. Temperature. Temperature has a direct impact on microbial activity. Higher temperatures generally increase the rate of microbial metabolism, leading to better flock formation and improved settleability, lower SVI. Lower temperatures slow down microbial activity, resulting in weaker flocks and higher SVI values. D. pH. The pH of the wastewater affects microbial activity and the chemical characteristics of the sludge. Extreme pH values, either acidic or alkaline, can cause the breakdown of flocks and reduce their settleability, leading to higher SVI values. A neutral pH around 7 is generally optimal for flock-forming bacteria and results in better settling of sludge. E. Organic loading, food to microorganism ratio, F4M ratio. The FM ratio plays a significant role in the quality of the sludge. A high FM ratio indicates that the system is overloaded with organic material, which can lead to the formation of less stable and less dense flocks, resulting in higher SVI. A balanced FM ratio ensures optimal microbial growth and flock formation, leading to better settling and lower SVI values. Star F. Chemical additives, coagulants, and polymers. The use of coagulants and flocculants can improve the settleability of sludge. Chemicals like alum, ferric chloride, or polymers are sometimes added to aid in flocculation and enhance the formation of denser, more compact flocks, thus lowering the SVI. However, excessive use of these chemicals can cause overflocculation and may lead to poor settleability if not properly controlled. G. Salinity. The presence of high levels of salts in the wastewater, high salinity, can affect the microbial activity and the structure of the flocks. High salinity can cause flock dispersion, resulting in poor settling and higher SVI. H. Presence of inhibitors or toxic substances. Toxic compounds or inhibitory substances, such as heavy metals or industrial chemicals, can affect microbial activity and flock formation. This may result in the formation of weak flocks that are more difficult to settle, leading to higher SVI values. 2. Interpretation of SVI. Low SVI, typically 100 milliliters per grams, indicates good settleability of the sludge, suggesting efficient biological treatment and well-formed flocks. High SVI, typically 150 milliliters per grams, indicates poor settleability, suggesting weak or dispersed flocks that may lead to issues such as sludge carryover into the treated effluent. 3. Summary. The sludge volume index, SVI, is influenced by factors like microbial composition, sludge age, temperature, pH, FM ratio, chemical additives, salinity, and the presence of inhibitors. By optimizing these parameters, wastewater treatment plants can achieve better sludge settleability, improve treatment efficiency, and reduce operational challenges related to sludge handling. Let me know if you'd like a diagram or further details on how to control or optimize these parameters for better SVI management. Q17. Explain the relationship between low FM ratios and high sludge age. 1. Food to microorganism, FIM ratio. The FM ratio is the ratio of the amount of organic food, usually measured as BOD or COD, supplied to the microbial population, measured in terms of biomass or microorganisms. A low FM ratio indicates that there is a small amount of organic food available relative to the microbial population, meaning that the microorganisms have to work harder to consume the available organic material. 2. Sludge age, mean cell residence time, MCRT. Sludge age refers to the average time that microorganisms, bacteria, stay in the system before being removed. It's often referred to as mean cell residence time, MCRT. A high sludge age means that microorganisms are retained in the system for a longer period, allowing them more time to break down organic matter and form biomass. A longer sludge age typically leads to the formation of more stable and well-formed flocks that settle better in the secondary clarifiers. Hazard 3. Relationship between low FFM ratios and high sludge age. When the FM ratio is low, there is less organic matter available for the microorganisms to consume. As a result, the microorganisms work more slowly, and the sludge age increases, because the system allows more time for microbial growth and maintenance of biomass. Low F5M ratio and high sludge age often go hand in hand because when less food, organic matter is available, microorganisms are not rapidly proliferating and their retention time in the system increases. This allows them to use the available organic material more efficiently and to be retained in the system longer. In practice, this leads to slower growth of microorganisms, meaning fewer but more mature microorganisms are present in the system. More stable microbial populations that are more resilient and capable of effectively breaking down organic matter over time. Lower waste production, because microorganisms are in a maintenance phase, utilizing less food, maintaining their biomass, which results in better sludge settleability. Number 4. Impact on treatment performance. Dictastani a slow FM ratio can lead to better treatment performance in certain situations, particularly when the system is designed to remove persistent organic material. The biological treatment process requires a stable microbial community. However, if the sludge age is too high, the system may experience overgrowth of slow-growing microorganisms, leading to inefficient nutrient removal and increased sludge production, which can be problematic for disposal. High sludge age can also result in poorly settled sludge if the microbial community becomes too old or inefficient. Summary. Low FM ratio and high sludge age are related because both are a result of having less organic matter, food, available for microorganisms, leading to slower microbial growth and longer retention time. This relationship ensures a stable microbial population in the system, but requires careful management to avoid issues like excessive sludge production or underperformance in nutrient removal. Let me know if you'd like further clarification or a diagram to visualize this relationship. Sharnt okay Asana and Perbicator Exker and I made him bigger rounding in at the sea rain. May me the sail bar who strike promet expressivlath perbi over smain lunch freaking ango eager as a name to death. Outs to see or heard is us. Remember this iwais cave pogarate with Eronet equal Q18. Classify aerobic and anaerobic processes with examples. Aerobic and anaerobic processes are two main types of biological treatment processes used in wastewater treatment, and they differ in their oxygen requirements. Shazur. 1. Aerobic processes. Definition. Aerobic processes are those in which microorganisms break down organic matter in the presence of oxygen. Oxygen is supplied to support the metabolism and growth of bacteria, fungi, and other microorganisms that degrade organic pollutants. Key characteristics. Oxygen is required for microbial respiration. Microorganisms in aerobic processes convert organic matter into carbon dioxide, CO2, and water, H2O. These processes typically occur in aeration tanks, or basins where air is bubbled through the wastewater to maintain sufficient oxygen levels. Examples of aerobic processes. Activated sludge process. Working. Wastewater is mixed with microorganisms in an aeration tank where oxygen is supplied to facilitate the degradation of organic pollutants. Common use. It is widely used in municipal wastewater treatment plants and industrial wastewater treatment for removing organic matter, BOD, COD. Oxidation ditches. Working. A variation of the activated sludge process, oxidation ditches involve the continuous circular flow of wastewater through a long channel with aerators to promote microbial treatment. Common use used for large-scale treatment in municipal plants. Trickling filters. Working. Wastewater is passed over a bed of microorganisms attached to the filter media. The microorganisms degrade the organic material as the water flows over them. Common use. Effective for treating wastewater with moderate organic loading and for smaller scale systems. Sequencing batch reactors. Working. A batch process where wastewater is added to a treatment tank, aerated to allow biological degradation, and then allowed to settle before being removed. Common use. Suitable for both small and medium-sized wastewater treatment facilities. Applications of aerobic processes. Removal of organic matter and suspended solids, BOD, COD. Effective in treating municipal wastewater, industrial effluents, and food processing waste. Number 2, anaerobic processes. Definition. Anaerobic processes occur in the absence of oxygen. Microorganisms involved in anaerobic processes break down organic matter into simpler substances, typically producing methane, CH2, carbon dioxide, CO2, and other byproducts. Key characteristics. No oxygen is required for microbial metabolism. Methanogenic bacteria are the dominant microorganisms that facilitate the breakdown of organic material. These processes typically take place in sealed reactors or digestion tanks where oxygen is excluded. Examples of anaerobic processes. Anaerobic digestion. Working. Organic waste, such as sewage sludge, is decomposed by anaerobic microorganisms in a sealed environment, producing biogas, mostly methane and CO2. Common use. Used for sludge treatment in municipal wastewater treatment plants and for organic waste treatment in industries such as food processing. Upflow anaerobic sludge blanket, UASB. Working. Wastewater is passed upward through a bed of anaerobic sludge. The organic matter is degraded by anaerobic bacteria, and biogas is produced as a byproduct. Common use. Often used for high-strength wastewater, e.g., from food and beverage industries, and for treating sewage sludge. Anaerobic filters. Working. Wastewater flows through a filter media that is colonized by anaerobic bacteria. The bacteria break down organic matter without oxygen. Common use. Used for wastewater treatment where the organic load is high and oxygen is not required. Methane fermentation. Working. A type of anaerobic digestion specifically aimed at producing methane, biogas, by fermenting organic materials. Common use. Used in biogas plants for energy generation from organic waste. Applications of anaerobic processes. Used for sludge stabilization and energy recovery through the production of methane. Effective for treating high-strength wastewater, e.g., industrial effluent, agricultural waste. Used in landfills and biogas plants for organic waste treatment and energy production. 3. Comparison between aerobic and anaerobic processes. Aerobic process, anaerobic process for absence of oxygen. Oxygen requirement. Requires oxygen for microbial respiration. Occurs in the absence of oxygen. Byproducts. Mainly carbon dioxide, CO2, and water, H2O, mainly methane, CH4, and carbon dioxide, CO2. Microbial activity. Aerobic bacteria degrade organic matter. Methanogenic bacteria break down organic matter. Treatment efficiency. Efficient in reducing BOD, COD, and suspended solids. Efficient in sludge treatment and biogas production. Energy consumption. Typically energy intensive due to aeration requirements. Energy production, biogas, is a byproduct. Common use, municipal and industrial wastewater treatment. Sludge treatment, organic waste digestion, biogas production. Summary. Aerobic processes are ideal for general wastewater treatment, where oxygen is supplied to promote the breakdown of organic pollutants by microorganisms. Anaerobic processes are effective for treating high-strength organic wastes, stabilizing sludge, and producing biogas, which can be used for energy recovery. Let me know if you'd like further details or a visual representation of these processes. Q19. Define the hardness of water and explain its problems if not removed. Describe the lime soda process for softening water. 1. Hardness of water. Definition. Hardness in water is a measure of the concentration of dissolved minerals, primarily calcium, Ca Bast, and magnesium, Mg ions, as well as other divalent ions like iron, Fe Maya. These minerals form when water passes through rocks and soil, picking up these ions. Types of hardness, temporary hardness, caused by the presence of bicarbonates, CaHCO3 and MgHCO3. It can be removed by boiling the water, which causes the bicarbonates to precipitate out. Permanent hardness, caused by the presence of sulfates and chlorides of calcium and magnesium, e.g. CaSO4, MgSO4, and MgCl2. This type of hardness cannot be removed by boiling and requires chemical treatment. Measurement of hardness. Hardness is typically measured in ppm, parts per million, or milligrams per liter, milligrams per liter, usually expressed as CaCO3 equivalents for simplicity. 2. Problems caused by hard water if not removed. Hard water can cause a range of problems in both household and industrial applications. Scaling in pipes and boilers. Hard water leads to the formation of scale, calcium and magnesium salts on pipes, boilers, and heating elements, reducing their efficiency and lifespan. In boilers, scale formation can also cause overheating and even failure. Ineffective soap and detergent action. Hard water reduces the effectiveness of soaps and detergents, as the calcium and magnesium ions react with the soap to form insoluble salts, preventing it from lathering and cleaning properly. Staining of clothes and fabrics. The formation of insoluble salts can lead to stains on clothes, dishes, and surfaces. Increased energy consumption. Appliances like water heaters and boilers need more energy to function efficiently due to scale buildup. Hazard 3. The lime soda process for softening water. The lime soda process is a widely used method for softening water, which involves adding lime, calcium hydroxide, CaOH2, and soda ash, sodium carbonate, Na2CO3, to precipitate out the calcium and magnesium ions responsible for hardness. Steps in the lime soda process. Step 1. Lime addition. Lime, CaOH2, is added to the water. This reacts with the temporary hardness, bicarbonates of calcium and magnesium, to form insoluble precipitates, calcium carbonate and magnesium hydroxide, which can be removed by sedimentation or filtration. The reactions are as follows. CaHCO2 plus CaOH2, right arrow CaCO3, precipitate plus H2O. MgHCO2 plus CaOH2, right arrow MgOH2, precipitate plus CaCO3. This step removes the temporary hardness. Step 2, soda ash addition. Soda ash, Na2CO3, is then added to address permanent hardness caused by calcium and magnesium salts, e.g. calcium sulfate, magnesium sulfate. The soda ash reacts with these ions to form precipitates of calcium carbonate and magnesium hydroxide, which are then removed from the water. The reactions are KSO plus Na2CO3 CaCO precipitate, MgSO plus Na2CO3, Rito MgCO3 precipitate plus Na2SO4. This step removes the permanent hardness by precipitating calcium and magnesium ions as solid carbonates. Step 3. Precipitation and filtration. After the lime and soda ash have been added, the water is allowed to settle and the precipitates, calcium carbonate, magnesium hydroxide, are removed by filtration or sedimentation. Advantages of the lime soda process. Cost-effective. Lime and soda ash are relatively inexpensive chemicals, effective for large volumes. It is efficient for treating large quantities of water and removing both temporary and permanent hardness. High efficiency. It can produce water with very low hardness levels. Disadvantages of the lime soda process. Waste generation. The process produces a significant amount of sludge, calcium carbonate, and magnesium hydroxide, which requires disposal. Chemical use. The process uses large amounts of lime and soda ash, which increases operational costs. 4. Summary. Hardness of water is caused by the presence of calcium and magnesium ions, and it can lead to scaling, reduced cleaning efficiency, and damage to pipes and appliances. The lime soda process is an effective method for softening water by removing both temporary and permanent hardness through the addition of lime and soda ash, followed by filtration or sedimentation to remove the precipitates. This process helps in reducing hardness and preventing problems like scale formation, soap inefficiency, and increased energy consumption. Let me know if you'd like further explanation or diagrams to visualize the lime soda softening process.